There are many different tensors used to describe large deformations. But why are there so many different ways to describe deformation? And why can't we just stick with the familiar infinitesimal strain tensor epsilon that we know from linear continuum mechanics? This is exactly what we will explore step by step in this video. Before we talk about the three-dimensional case, have a look at this one-dimensional bar with undeformed length capital L. If we deform the bar homogeneously in the longitudinal direction and denote the length of the deformed bar as lowercase l, we have different options to quantify the deformation of the bar. For example, we can compute the stretch lambda, defined as the deformed length divided by the undeformed length. We can also compute the infinitesimal strain epsilon, which is defined as the difference of the deformed and the undeformed length divided by the undeformed length. When the bar is not deformed, the stretch is 1 and the strain is 0. When the bar elongates by 20%, the stretch is 1.2 and the strain is 0.2. With the stretch and the strain, we have two different measures of deformation. Both of them can be used to quantify the deformation of the bar. If I tell you the stretch of the bar is 1.2, you know exactly how much the bar has deformed. Similarly, if I tell you the strain of the bar is 0.2, again you have all the information you need for understanding the deformation of the bar. Okay, why am I telling you this? The point I want to make is that there's not only one possibility to characterize the deformation of the bar. In fact, there are infinitely many. For example, let's define a new measure of deformation c as the square of the stretch. I know computing the square looks a bit random, but this is again a valid measure of deformation. For example, if I tell you that c is 0.64, you have all the information you need for understanding the deformation of the bar. It doesn't matter if I give you the stretch, the strain, or the new measure c. Once you know one of these quantities, you can compute the other two because they are all related to each other. I'm bringing this up because there's some ambiguity in the way deformation is quantified mathematically. There are different choices and often there is no right or wrong. And this ambiguity becomes even more apparent in the three-dimensional description of large deformations, where we have all sorts of different tensors for describing deformation. For example, in large three-dimensional deformations, stretch is described by the right and left stretch tensors, squared stretch is described by the right and left Cauchy-Green tensors, and strain is described by the Green-Lagrange and Euler-Almansi tensors. Seeing all these tensors for the first time can be intimidating. Why are there so many different tensors and what do they mean? How do they differ and what do they have in common? And why the hell can't we agree on just one measure of strain as we do in the small strain theory? It took me a while to realize that there's really no reason to be intimidated. In this video I want to show you why. Okay, we have different options to quantify large deformations in 3D. Surprisingly, the deformation gradient f is not a good measure of deformation. Here you can see three different objects and the corresponding deformation gradient at the illustrated point. The green object is translating and we see that the deformation gradient does not change. The orange object, however, is translating and rotating, and we observe that the deformation gradient changes even though the object is not deforming. Let's investigate why this is happening mathematically. Translating and rotating an object in space without deforming it is called rigid body motion. A rigid body motion of the undeformed object can be mathematically described by a matrix Q multiplied with the undeformed point capital X plus a vector c. Q is a proper orthogonal rotation matrix which is constant in space, and c is an arbitrary vector, also constant in space. Here's an example of such a rigid body motion. Q is rotating the undeformed points around the origin, and C is shifting the rotated points in space. If we compute the deformation gradient of the rigid body motion, we find that F is equal to Q. This means that the deformation gradient depends on the applied rotation Q, and it is therefore not a pure measure of deformation. In the video about matrix decompositions, we have learned how to decompose F with the right and left polar decompositions. Let's apply the right polar decomposition to our example. F is decomposed into the rotation matrix R and the deformation matrix U, which is also called the right stretch tensor. In this example, F is equal to Q, which is a pure rotation. Therefore, we get R equals Q and U equals the identity I. This means that U does not change under rigid body motion of the undeformed configuration. If we compute U for our three objects, we observe that U indeed remains unchanged for the translating and rotating object. U only changes for the blue object, which is the only one that is really deforming. This means that the right stretch tensor U is a suitable measure of deformation. We can also compute the left stretch tensor V by applying the left polar decomposition. Because F describes a pure rotation in this example, V equals the identity. We observe that V remains unchanged under translation and rotation, making V another suitable measure of deformation. This means that now we already have two measures for quantifying deformation. And in the previous video about matrix decompositions, we have learned about their geometric and physical meaning. The stretch tensors U and V are directly related to the stretch that we know from the one-dimensional example. In fact, in 1D, U and V are scalars and equal to the stretch lambda. This means that in 1D there's only one measure of stretch, while in 3D we have two different possibilities to describe stretch. This is because in 1D there are no rotations, but in 3D there are rotations, and when we decompose the deformation gradient into stretch and rotation, we can choose whether we want to have the stretch applied first, followed by the rotation, or vice versa, which leads us to two different measures of stretch. Now, before we talk about other measures of deformations, we need to talk about an important difference between U and V. One of these tensors behaves in an unusual way, a counterintuitive behavior that you probably wouldn't expect for something that is called a stretch. Let me explain what I mean. We already know that U and V do not change when we apply a rigid body motion to our undeformed object. But here comes the twist. If we first deform our object and apply a rigid body motion afterwards, something strange happens. The right stretch tensor does not change, but the left stretch tensor does. Isn't this weird? We are not deforming the object any further, so shouldn't both stretch tensors remain unchanged? To understand why this is happening, we have to understand what a rigid body motion of the deformed configuration means mathematically. Let's assume that the object has been deformed until time t equals 1. Recall that the deformed point is denoted by lowercase x. Now we apply a rigid body motion to the deformed object and denote the position of the new point by x with a small circular arrow. A rigid body motion of an already deformed configuration can be mathematically described as a proper orthogonal rotation matrix Q times the deformed point lowercase x plus a constant vector c, which gives us the point x arrow after both deformation and subsequent rigid body motion. Here lowercase x is the deformed point at time t equals 1, that is the time at which the deformation ends and the rigid body motion starts. Q and C are independent of space. The deformation gradient f arrow after both deformation and subsequent rigid body motion is the gradient of x arrow, which is equal to q times f, where f is the deformation gradient after the deformation but before applying the rigid body motion. After having derived the deformation gradient f arrow, we can investigate how it decomposes into rotation and deformation. Let's substitute the right polar decomposition of f. We obtain q times r times u. Eventually we want to decompose f arrow into a pure rotation matrix r arrow and a pure deformation matrix u arrow. This is straightforward if we set r arrow equals to q times r and u arrow equals to u. We see now that the right stretch tensor u does not change when we apply a rigid body motion to the already deformed object. So let's try the same for the left stretch tensor v. First we substitute the left polar decomposition of f. And now we run into a problem. We cannot simply multiply q and r to obtain a new rotation matrix as we have done previously, because v is in between these matrices. Instead we must apply a trick. We substitute q transpose q, which is equal to the identity. Now we can decompose f arrow into a pure deformation matrix v arrow and a pure rotation matrix r arrow, where v arrow is qv q transposed and r arrow is qr we observed that the left stretch tensor is not the same before and after the rigid body motion. It seems that different tensors react differently to rigid body motions of the deformed configuration. Tensors like U that are invariant to such rigid body motions are called Lagrangian tensors. You can think of these tensors as tensors that are in some sense related to the undeformed reference configuration, which means that they are not affected by rigid body motions of the deformed configuration. On the other hand, we have Eulerian tensors like V, which are related to the deformed current configuration, which means that they change upon rigid body motion of the deformed configuration. Finally, there are also tensors like F, which are related to both the reference and the current configuration. These tensors are called two-point tensors. Like the Eulerian tensors, they also change when we apply rigid body motion to the deformed configuration, but the formula describing these changes looks slightly different. Let's summarize. We have learned that the stretch tensors U and V do not change when we apply a rigid body motion of the undeformed configuration. But when we apply rigid body motion to the deformed configuration, the Lagrangian tensor U remains unchanged, while the Eulerian tensor V changes. Here's some food for thought. If you want to establish a relationship between the deformation and the stress in a solid material, would you rather make the stress depend on a Lagrangian or Eulerian measure of deformation? Let me know what you think in the comments. Okay, we know quite a lot about the right and left stretch tensors now. But as I said in the beginning of the video, in the theory of large deformation kinematics, we can define many different measures of stretch and strain. In the following, we will discuss some of the most popular ones and learn why some of them are more commonly used than the stretch tensors U and V. We start off with the so-called right and left Cauchy-Green deformation tensors. The right Cauchy-Green tensor C is defined as F transposed F. This definition might look a bit arbitrary at first glance. Its interpretation becomes clearer when we apply the right polar decomposition to both f's in the formula. If we rearrange the formula a bit, we get the term R transposed R, which is equal to the identity by definition. What's remaining is U transposed U. Because U is symmetric by definition, U transposed U equals U times U, which we can also write as U squared. Now this is interesting. C is the square of the right stretch tensor. Remember that in 1D we squared the stretch and we didn't lose any information about the deformation. With the right Cauchy-Green tensor we extended this idea to 3 dimensions. Because C depends only on U and not on R, it is a pure measure of deformation and invariant to rotations, which becomes clear if we compute C for our 3 examples. One reason why C is a popular measure of deformation is that it can be computed quite easily for a given deformation gradient. The right stretch tensor U is not as easy to compute. U is the square root of F transposed F. We will not talk about this in detail, but computing the square root of a matrix is not straightforward because it involves solving an eigenvalue problem. Of course, such operations are implemented in most software libraries for scientific computing, but still it is much easier and computationally efficient to compute C, which is just F transposed F without a square root. While talking about the right Cauchy-Green tensor, you may have guessed already that there is also a left Cauchy-Green tensor. The left Cauchy-Green tensor B is defined as F times F transposed. When we apply the left polar decomposition to F, we find that the left Cauchy-Green tensor is equal to the square of the left stretch tensor. The difference between the right and left Cauchy-Green tensors is that one of them is a Lagrangian and the other one is an Eulerian tensor. This becomes clear when we apply a rigid body motion to an already deformed configuration. Using the fact that Q transpose Q is equal to the identity, we find that C arrow is equal to C. This is not possible for the left Cauchy-Green tensor, for which we find that B arrow is equal to QB Q transposed. So C is a Lagrangian tensor, while B is an Eulerian tensor. Note that in the one-dimensional case, where we have no rotations, C and B are both equal to the squared stretch. Finally, note that C and B also have interesting geometric interpretations regarding the length of the undeformed and deformed line elements. This becomes clear when we compute the scalar product of the deformed line element with itself. We substitute d lowercase x equals f times d capital X, and after some rearrangements, we find that this is equal to d capital X transposed times c times d capital X. Okay, I admit that it is not immediately clear how this formula helps us to interpret C. So let's reformulate this expression a bit by introducing the C norm, which is defined like this. If we substitute this into our expression, we find that the norm of a deformed line element is equal to the C norm of the corresponding undeformed line element. This means that C helps us to relate the length of an undeformed line element to the length of the deformed line element. If C is large, then the length of the deformed line element is large and vice versa. We can also derive a similar relationship for the left Cauchy-Green tensor. Specifically, the inverse B norm of a deformed line element is equal to the norm of the corresponding undeformed line element. So if B is large, its inverse is small, and thus the length of the deformed line element must be large compared to the length of the undeformed line element. Did you notice that I didn't call any of the tensors that we discussed so far strain tensors? Remember that in 1D the stretch was 1 in the undeformed configuration, while the strain was 0. The tensors u, v, c and b all have in common that they are equal to the identity in the undeformed reference configuration. This distinguishes them from strain tensors, which are measures of deformation that are 0 in the undeformed configuration. The most popular strain tensor is the Green-Lagrange strain tensor E, which is defined as 1/2 C minus the identity tensor. Because this tensor depends on C, it is a measure of deformation that is invariant to rotations. And because we subtract the identity from C, the tensor E is 0 if there is no deformation. You might wonder why we include the factor of 1/2 in the formula. As I will show you now, including this factor gives the strain tensor a particularly meaningful interpretation. Specifically, I will show you that the Green-Lagrange strain tensor is closely related to the strain tensor that you know from linear continuum mechanics. To understand this, we first need to take a step back and define the displacement, which will allow us to express the Green-Lagrange strain tensor in an alternative form. Recall that a point in the undeformed reference configuration is denoted by capital X, and a point in the deformed current configuration is denoted by lowercase x. The displacement u is defined as the difference between the deformed and the corresponding undeformed point. It is a vector that points from the undeformed point to the deformed point. If we substitute the deformation mapping for lowercase x, we get u as a function of capital X and t. The derivative of this function is called the displacement gradient. It is equal to the deformation gradient f minus the identity I. If we rearrange this, we find that f is equal to the displacement gradient plus I. And we can use this expression to express the Green-Lagrange strain tensor in an alternative form. First we substitute the formula for the right Cauchy-Green tensor, and then we substitute the displacement gradient plus the identity of f. After some rearrangements, we arrive at this expression. Maybe you can recognize the first term in this expression. It is equal to the infinitesimal strain tensor epsilon that we know from linear continuum mechanics. So the Green-Lagrange strain tensor seems to be somehow related to the infinitesimal strain tensor. If you've watched my video on the infinitesimal strain tensor, you may remember that we defined it in such a way that it is 0 for rotations, like the one you see here. The problem is that what you see here is actually not really a pure rotation. If you look carefully, you will see that the cube is slightly changing its size. The rotation that you see here is only a rotation if we assume that the deformation is really small. This means that when we derived the infinitesimal strain tensor, we made an assumption. We assumed that the deformation is small. As a consequence, the infinitesimal strain tensor is only invariant to rotations when this assumption is applicable. For larger deformations, the infinitesimal strain tensor is not invariant to rotations. For example, if we compute the infinitesimal strain tensor for our previous examples, we see that it changes even when the object is not deforming. The Green-Lagrange strain tensor can be interpreted as the strain tensor that you know from linear continuum mechanics, plus a correction term that makes sure that the strain is invariant to rotations even for large deformations. So if we compute the Green-Lagrange strain tensor for the same examples, we see that it is not changing upon rotation. The Green-Lagrange strain tensor depends on the right Cauchy-Green tensor. Alternatively, we can define a strain that depends on the left Cauchy-Green tensor, the Euler-Almansi strain tensor lowercase e. It is defined as 1/2 I minus the inverse of b. The Green-Lagrange strain tensor is a Lagrangian strain tensor, and the Euler-Almansi strain tensor can be interpreted as its Eulerian counterpart. Finally, note that in one dimension the Green-Lagrange and Euler-Almansi strain are not equal. Only when the deformation is small, both of these strains converge to the infinitesimal strain epsilon. Let's summarize. We started this video by talking about the right and left stretch tensors u and v. Both of them are invariant to rigid body motions of the undeformed configuration. However, only the right stretch tensor is invariant to rigid body motions of the deformed configuration. Afterwards, we have defined the right and left Cauchy-Green deformation tensors, which are the squares of the stretch tensors. They can be seen as alternative measures of deformation, which are easier to compute because we do not have to compute the polar decomposition explicitly. Finally, we introduced the Green-Lagrange and Euler-Almansi strain tensors and learned that they can be seen as modifications of the infinitesimal strain tensor to make sure that the strains are invariant to rotations. I know this entire topic can be very confusing, so please let me know if you have any questions. That's all for today, see you in the next video, bye!